All right, welcome to another worked example with Dr. Schley. So last week we looked at a quiz where we considered an electron entering this electric field, and you can see that it experiences a force and it accelerates upwards. And we kind of worked through that. And eventually we were asked to consider why we could sort of ignore the gravitational effects, why the calculation does not need to include gravitational effects. And it's really because the electron is so low in mass that if you do the calculation, if you calculate what the weight of the electron would be, you realize that it's so tiny that even if you did subtract it from the electric force, it still is basically just the electric force acting on it. The weight is negligible. Now this week, we see a very similar looking question, and paper 2, sets you up to sort of help you through the ideas in the calculation. Like one idea leads to the next. And so right away, they have you consider two types of fields, right? A gravity field and an electric field. State the property of an object that experiences a force when the object is placed in both a gravity field and an electric field. If you remember that the strength of a gravity field we call local G, and we can think about it in terms of Newton's second law, like the weight, the force of gravity equals mg. Sometimes we use W for this, right? Weight equals mg. Well, G is the local gravity field strength. And so we can rewrite it as the ratio of force to mass. We've been studying electric fields, and we said an electric field is a region of space. The electric field is a region of space where a charge experiences a force. And the strength of the field is like how much force per unit charge, right? And so if you think about that, you can say, the question is asking me for a property of an object that experiences a force when it's in an electric field. Well, the property of the object that experiences a force in an electric field is charge. And using that sort of analogy, we said there's a powerful analogy we can draw with, massive objects in gravity fields and charges in electric fields. The mass is the property of the object that experiences a force in a gravity field. So the answer that you should have written down on this line would be mass, right? Sort of thinking about like, oh, mass experiences a force in a gravity field. Charge experiences a force in an electric field, right? So mass for a mark there, charge for a mark there, and really there's no other correct answer than that, okay? If you didn't get those marks, but this idea right here is making a lot of sense to you, then awesome, right? That's what we do. We learn, from our mistakes. So I didn't get that right, but now I'm learning. All right, the paper goes on to have us calculate some things here. Like I said, it's not trying to trick you. It's trying to sort of, help you here, one calculation leading to the next. Calculate the magnitude of the electric force acting on the particle in the field. Okay, so let's clear all that off, all of it. So now it's saying, all right, let's just consider the electric force, okay? We're only going to consider the electric force right now. It's helpful sometimes to preview sort of what are all the calculations before me. So if you didn't already like flip the page over and look at, oh, there's 4 marks here coming up. And it says by considering the resultant vertical force. So resultant remembers the vector addition, the sum of the vector addition. So we have to add some force vectors, but only in the vertical direction. Show that the acceleration is this. And it even says in the electric and gravitational fields. It's reminding you like, hey, 2 fields here. This thing has both mass and charge, right, as it enters the field. But first, we're only going to calculate the up force, right? The electric force is the thing that's pushing this thing up. There's a few ways to sort of think about that. One is that it's accelerating that way. And so there must be a net force sort of upward. Weight makes things go down. We can also think about this is the positive plate. The top metal plate is connected to the positive terminal of our sort of voltage source here. So this is the negative plate, and this is a negative charge, right? So the charge is negative 4.2. So as it enters this field, it's repelled by the negative plate, and so it moves that way. For just review, we could draw a couple of field lines, and we'd try to make these evenly spaced, and we'd say, well, a proton or a positive charge would move in this direction. And so the direction of the field is down, and that's why a negatively charged particle moves up, right? Or accelerates that way. All right. So let's go ahead and calculate that there electric force based on information that's given there. We know how to calculate the strength of the electric field as the voltage divided by the distance. They give you the distance, they give you the voltage, and so we can get this number. Remember that it's also equal to the force per charge, as we mentioned a moment ago. And so we can rewrite this. If force is the thing that we're solving for, we can rewrite it as VQ over D. That's the same thing as, V over D is just E, so it's the same thing as EQ. All right, so the force is EQ. You can either think about it as calculating the electric field first and then multiplying it by charge, or just multiplying it all together. We saw the same sort of working last week. So 1.2 by 10 to the 3 volts times the given charge of 4.2 by 10 to the negative 9 coulombs. If you want the negative in there, you can keep it. And then we have 3.6 centimeters, so 0.036 meters, right? We need to convert that to meters. All right, everybody that's following along at home has their calculator handy. I'm going to show this on the screen here for the benefit of everybody. It's just like, oh, I'll let you do the calculation. Let's just see it. So we got 1,200 volts times, I like to use parentheses even when I don't need to, 4.2 by 10 raised to the negative 9. There's my numerator divided by 0.036. Note that I lose the richness of knowing what is the field strength by just multiplying it this way. By doing the numerator divided by the denominator, I know that the final force is 1.4 by 10 to the negative 4. 1.4 by 10 to the negative 4 newtons, right? Because I'm solving for force. If you wanted to calculate the electric field first, you divide these two, you get a number for E, and then multiply it by the charge. You'll get the same answer, but you'll also know sort of what the field strength was. If they asked, for what is the strength of the field, then, you would have to calculate it that way, separate out your answers. So that's the force that's pushing it upward. And since we already kind of previewed the paper here, we know what we're going to have to do for this one, and even give us good clues in the wording of the question there. So if we just kind of read through this, the resultant vertical force, it's like we're using Newton's second law. The sum of the forces equals ma. They give us the mass. They ask us to consider the sum of the forces, right, the resultant force, and they tell us that we should calculate A as 14 when we do that. Let's draw a free body diagram. So here's our charged particle, and there's a force down called weight, that's equal to mg, and there's a force up, the electric force acting on this charged particle in the uniform electric field, which we've already calculated as 1.4 by 10 to the negative 4 newtons. All right, so we know that that's, and we know that that's the stronger force because we can see which way it accelerates, right? Like the net force is the direction of acceleration and it curves upward, right? So there's a net force acting up that's making the charge sort of move that way. All right, let's calculate the weight. You may recall that the mass is 5.9 by 10 to the negative 6 kilograms, right? So the mass is given, and G is 9.81 newtons per kilogram here on Earth. Let's do that calculation also on the screen there, over here. All right, so we've got 5.9 by 10 raised to the negative 6. It's that number times 9.81 for a weight of 5.79, we'll round it, by 10 to the negative 5, right? 1, 2, 3, 4, 5. So with the paper that we did last week that I showed at the beginning of this video, the mass was 10 to the negative 31 for an electron. So even when you multiply it by, 10 in order of magnitude, it's still 10 to the negative 30. And that is so tiny that even if you did subtract it, the calculator is basically going to say, well, yeah, there's a change way out here, 30 decimal places, but it's negligible. Here, this is just, they're close enough that we do have to consider it. So the sum of the forces in the vertical direction is going to be, well, this is the bigger number, right? We already kind of knew that. It's accelerating upward. So we're going to subtract that away from it. So in my calculator, I'm just going to make this value negative and then add the electric force to it, 1.4 by 10 raised to the negative 4. So the resultant vertical force is this number. some of the forces in the y direction. So again, using Newton's second law, we've got 1.4 by 10 to the negative 4 newtons. The electric force opposing it is the 5.79 by 10 to the negative 5 newtons of weight, for a net force or a resultant force of 8.21 by 10 to the negative 1, 2, 3, 4, 5 newtons. And that's going to accelerate our 5.9 by 10 to the negative 6 kilogram mass, right? F equals ma, a certain amount. So if we divide both sides by this, right, then we'll have the acceleration, and this should be a number that's close to 14. So I've got that in my calculator still. Divide it by the mass, open parentheses, 5.9 10 to the negative 6. And I get a number there, 13.92 meters per second squared, and that is indeed about equal to 14. So you want to kind of show something like that in your working there, but you know, present it in such a way like you don't have a calculator on your paper, right? So you can kind of lay that all out there and make it very clear, sort of your final answer, and you know, lay it all out in a nice, neat fashion there. All right, the question goes on to ask us to determine the time that it's going to take the particle to move from x to y and the distance p from point y from the left-hand edge of the top plate. So the time and the distance p, let's go back up to the figure and maybe work through that. It has uniform velocity. It's like, we probably should be able to use the range equation to solve for this. So let's remind ourselves, like, this is a horizontal displacement. It's like range equals vxt. And we're given vx, and they ask us to calculate t. So as soon as we know the time, we'll be able to calculate p very readily by just multiplying whatever we get for t by 0.75. So like, we know how to calculate that one. The troublesome thing is, how do we calculate time? Well, we know it's crashing into this plate. The last paper that we did, it didn't quite make it there. So we're using some physics to say, well, what is the displacement? Well, here we know what the displacement is going to be. It's taking a certain amount of time for this thing to move 1.8 centimeters this way, right? So there's a net force that's making it accelerate. And we know that acceleration is like 13.92 or whatever. So we should be able to calculate the distance that it's going to travel is equal to its initial velocity times time plus 1/2 acceleration times time squared. Now this quadratic would be tough to solve. Thankfully, there's no initial velocity in the y direction, right? So this term basically goes away. The initial velocity in the y direction is 0. The displacement is 0.018 meters, right? It only has to go that distance. How much time does it take to travel this 1.8 centimeters is what we want to solve for. So something that needs to move this much, that accelerates at 13.92 meters per second squared, will have to travel for how long in order to go that far? That's what we're sort of solving with this, right? I'll leave it as an exercise for the YouTube viewers to do this calculation on your own. So it's 0.018, and we're dividing it by 1/2, and then we're dividing it by 13.92, and that's what t squared is equal to. So don't forget to take the square root of that to realize it is a time of 0.05, and if you want to round that to 1, you could, seconds. 0.051 seconds, 0.0508 is what my calculator shows. Make sure you're getting the same thing in your own calculator at home. Now we need to calculate the range, and as we said, once we got the time, there's no trouble to solve that. 0.75 meters per second of velocity for 0.051 seconds is how many meters? 0.75 times 0.051. I get 0.038. So you could say P is about 0.04 meters, or about 4 centimeters. 0.038 meters, something like that. and one or two significant digits. That actually might be the better answer. 2 significant digits, 0.038 meters. I think that's the last one there. Plenty of time to spare. 12 marks on that. All right. If you found this calculation to be pretty awesome, check the link above for the quiz that I was alluding to earlier. And don't forget to get on the Dr. Schleich notification squad. If you enjoyed the video, smash that like button, and it's only a matter of time before the merch shop is open. We'll see you next time.